Hello everyone, welcome to an AP Explained video. Today we are going over Unit 1 of AP Physics 1 Algebra Base Kinematics, and this video is to serve as a quick review for the upcoming AP exam in May. So the main learning objectives of this unit is basically, are you able to describe motion using position, velocity, and acceleration, analyze motion using graphs and equations, apply kinematic equations in 1D and 2D, and interpret motion diagrams qualitatively. So the main thing in kinematics is knowing the difference between what is scalar and what is vector. Scalar is something that only has magnitude but no direction, and a vector is something that has magnitude and direction. So a scalar example could be position, speed, or time. All of these things have magnitude, so 5 meters, 5 meters per second, 5 seconds, all of these have a magnitude. But if we go over to the vectors, we have displacement, velocity, and acceleration. Displacement can be 5 meters or negative 5 meters. The velocity can be 5 meters per second or negative 5 meters per second. And the acceleration can be 5 meters per second squared and negative 5 meters per second squared. As you can see, the main difference is that the vectors can be negative, indicating that they have a motion in the opposite direction of the origin. So main thing to remember is vector, a quantity that has both magnitude and direction, and a scalar has only magnitude but no direction. Average versus instantaneous velocity is something that is very important to know in kinematics. The velocity average is the delta x over the delta t, which is just the change of position over the change in time, and the instantaneous velocity is the slope of the tangent line on the position versus time graph. So if we look at this graph here, we can see that we have 2 points highlighted. We have 5 seconds and 30 meters and 3 seconds and 20 meters. And if I were to tell you to calculate the average velocity between 3 seconds and 5 seconds, you would probably go ahead and go with delta x over delta t. And you probably plug it in as you would for slope form as the final position minus the initial position over the final time minus the initial time. And doing this, we would plug in our final position, which is 30. So 30 minus our initial, which would be 20, over our final time, which corresponds with the 30 meters, is 5 seconds, minus the 3 seconds that corresponds with the 20. Doing this, we would get 10 over 2, which simplifies to 5 meters per second. So that average velocity from 5 from 3 to 5 seconds is 5 meters per second. But if I were to ask you what the instantaneous velocity is, then you would be wondering, what's the difference? Well, the difference is that the instantaneous velocity is the slope of tangent on position versus time graph. This may be weirdly worded, but the slope of the tangent is basically at what point does it hit the graph once and never again. So the slope of the tangent at this case would be this little line right here. So let's say this is the graph right here. This is the tangent. Let me do that in a different color. This is the tangent. So this is the tangent. It hits only here and there. So that's the instantaneous velocity at, let's say, 3 seconds. That's the instantaneous velocity. And this is a very good example because we can see from here, from 3 seconds to 5 seconds, we said that it would be 5 meters per second, the average velocity. But if we look over here at 4, if we make a tangent line over there, we can clearly see that the slope of the tangent line is 0, indicating that there's no velocity at that point. So even though we have 5 meters per second between 3 seconds and 5 seconds, that doesn't mean the whole time we're going 5 meters per second, sorry. That doesn't mean we're going 5 meters per second the whole time. Because as we can see at 4, we have a slope of 0. So main thing I'm saying is that average velocity and instantaneous velocity are not the same thing, and make sure to pay very close attention to that. Here we have our kinematic equations, and these are all equations that you can use when you have constant acceleration. And only time you can use this is constant acceleration. So if you have a question that's talking about acceleration changing, acceleration increasing at like increase doubling every second, you cannot use this equation. This has to be constant acceleration. So here we have v final is equal to v initial plus the acceleration times time. And then here you have delta x, which is the displacement, is equal to v initial times t plus 1 over 2 at squared. And a is acceleration, t is time. And then here we have delta x, which is displacement again. And then here we have this v by itself. And in most textbooks, you'll either have v final to indicate final velocity, or you'll just have a v by itself to indicate final velocity. But almost always they will have a velocity not zero to indicate initial velocity. And that's v final plus v initial over 2 times time. And then the last but not least, we have v final squared equals v initial squared plus 2 times acceleration times delta x. Next up, we have motion graphs, which is something that's very important in kinematics, and it can determine a lot about our object. So here we have a position versus time graph, and we can see we have three different graphs. Over here, we have a position versus time graph that has a constant slope of 0, and since our slope is equal to our velocity, that means we have a 0 velocity, and since our velocity is 0, the position stays the same as time increases since we're not moving. And here we have a constant slope, meaning we have a constant velocity. So as time increases, our position increases at a constant rate. And over here, our slope is not constant and our slope is increasing as time increases. So that means our position versus time graph is going to increase more and more as time goes on because our velocity is not constant, and that is due to acceleration. And as we said earlier, the velocity is the vector quantity of speed, and speed is the scalar quantity of velocity. So taking the absolute value of velocity gives us speed. And here, a velocity versus time graph, as we said before, acceleration causes the slope of the velocity to increase at a constant rate, causing the position versus time graph to have a parabola type shape. And since the slope is equal to acceleration, then we know if we have a zero acceleration, we're going to have a zero slope for the velocity because the velocity is going to be the same. Um, and here, if we have a flat graph, we can see that the acceleration is constant, showing that the velocity stays the same throughout the whole time as time increases. And here we can see the area under the curve is displacement. So if I take the area under this curve, making this a triangle, and I take the area under this curve, I would get the displacement. And if I take the area under this curve, I would get zero displacement since we have zero velocity as our slope. It is equal to zero. And here we can have the acceleration is equal to zero. And if I take the area under this, we'd have just the displacement for a constant velocity. And here we have acceleration versus time graph. The slope is equal to jerk, which is technically not important for AP Physics 1, which I thought was just something interesting. And the area under the curve would be the change in velocity. And here we have just taking the area under this, so making a line, taking this area, and you'd get the change in velocity. And over here we have 0. And the reason we have 0 is because the acceleration is 0, so the velocity would not change, it would stay constant. So taking the area under that would give you nothing. And if I did not mention it over here, the absolute value of acceleration is equal to the magnitude of acceleration. So the scalar quantity of acceleration would be just the magnitude, and the vector of magnitude of acceleration, just acceleration with the direction. Free fall is something very important to understand, especially in Unit 1, that the acceleration in free fall is equal to the gravity, which is equal to 9.8 meters per second squared downward. So no matter which time and position, if we're on Earth, the acceleration is always pulling down on the object at 9.8 meters per second squared. And since the acceleration is constant, we can use the kinematic equations that we discussed about earlier here. Since we have constant acceleration, we can use any of these equations for the free fall questions, and we will get them 100% right. Next up is free fall. Free fall is something that is very important to understand in Unit 1 of kinematics. Acceleration is just equal to gravity because gravity pulls everything down as you throw it up. So the gravity is equal to 9.8 meters per second downward. And since the acceleration is constant, which is equal to gravity, we can use these equations that we made earlier for constant acceleration. These will work for free fall equations, and you will get them 100% right of the time if you're using the correct variables. And during upward motion, the acceleration is equal to negative g, which is something to keep in mind. And this information right here at the top, the velocity is equal to 0, but the acceleration does not equal 0. The acceleration is still gravity, which is constant throughout the whole time. It's something that is very, very important for calculating the time or displacement of an object during free fall. And then we have 2D motion and the components of it. So here you would split your velocity components into the x and the y direction. And this is very helpful for free fall, as we mentioned earlier, and projectile motion. So with free fall, not free fall, with this 2D components, you would take this velocity, right? And you would take this vector that we're used to seeing in 1D. So we'd have just going into the y direction or then the x direction. But now we can split this into x and y components using the SOHCAHTOA. And if we take sine of theta, which is opposite over the hypotenuse, we would get Vy over velocity. And if we take the theta of here and use cosine, we get adjacent over hypotenuse, which is Vx over V. And if we take tangent of theta, we get Vy over Vx. And then we can use that to manipulate the equations to solve for Vy. So we multiply by V, multiply by V, and these will cancel out. So then you have Vy is equal to V sine theta. And to make that more sense, let's say for example, cosine of theta is equal to Vx over V, and I want to calculate for the Vx. What I would do is just multiply this by V, multiply this by V. These will cancel out, giving me V cosine of theta is equal to Vx. And then using this information, we can plug in this velocity in the x into this x component direction. And once we do that, we can get time, which does not have an x or y. Time is the same in both x and y directions. And we can plug this time into the y equations, and then we can solve for our unknowns. And in the x and the y direction, they are the same exact equations. Only difference is that we are adding the subscript x, notifying that this is the value in the x direction and in the y direction. So some common mistakes is mixing up the x and the y components, which is something many people do, especially with the projectile motion and free fall. That's when I would suggest writing out your variables and your knowns and unknowns to make it more organized. Forgetting direction and the signs, that is something that you should not do, because if you do forget your signs, your answer will be completely wrong. And to fix that, I would define your coordinate system first. So discuss whether north is positive, south is negative, east is positive, west is negative. Just defining that would be very helpful. And then make sure you only use kinematic equations if acceleration is constant. This is something that's very important because you cannot use kinematic equations if your acceleration is changing. It should be a constant value throughout the whole time that you use it. So a quick summary is that motion is just position, velocity, and acceleration of an object. Scalar is magnitude in no direction. Vector is magnitude and direction. The graphs show full motion pictures, so you should be able to get everything that you need from the graphs. And that kinematic equations require constant acceleration. I don't know how much more I need to stress this out, but you need constant acceleration. And you should always check your units and directions when you are putting in your variables into the equation, because you could be solving the whole time in meters and it's asking you in centimeters and your answer is a whole decimal place off. So that is something to very much be careful of. So guys, that will be the end of this video. So this is the end of unit 1. Next up will be unit 2, dynamics, forces and Newton's laws. I will make sure to get that video up soon. And if you did enjoy this video or found it helpful, please do share, like, subscribe, comment down anything that you believe I should make a video on, and I will try to respond to every single one. Thank you guys and have a good day.